All right, so we just looked at this equation for an ellipse and all of the properties of an ellipse and how we could either, given an equation for ellipse, come up with the key points about the graph and sketch a graph, or given information about the graph, like in the example on the screen here, the vertices and the foci, how we could then generate an equation for an ellipse. Now, again, looking from what I see in the book may stick to just these things being centered at the origin. You could always get these exact same formats if you just shifted the away from the origin by having x minus some h value and y minus some k value in the equation. Now, we don't need to have 4 different formats of the equation like we did with the parabola, but I will point out something while we still have this here. It is possible that the ellipse might be wider from top to bottom than it is from side to side. And so the examples that we did, the foci were along the x-axis, but you could certainly have it oriented up and down, and the foci could be along the y-axis. And the only thing that would change that you could imagine here is that since A is the major axis length, well, now the major axis would be in the y direction. So I'm going to put that you could have y squared over a squared plus x squared over b squared if it's bigger horizontally. So then you'd have, something like this, where you had foci this way. If you have something like that, then the A direction will be vertical instead of horizontal, and that means that it's in the y direction, so the a squared will be under the y instead of being under the x. And so that's the only difference, is you switch the x and the y positions in the 2 fractions so that the y is on top of the bigger a squared value and the b is on the smaller one. And so remember, since a squared equals b squared plus c squared, a will always be larger than b. And so if I was given an equation, it doesn't, since this is a plus, it doesn't really matter which way they're written. So for example, if I have x squared over 16 plus y squared over 25 equals 1, well, then you would want to take note of the fact that the number under the y is larger than the number under the x. And that means that that's the a squared value. So that a is equal to 5 and that b is equal to 4. And that means that the ellipse is an oval that's sort of up and down instead of side to side. That it's 10 from top to bottom and only 8 from side to side, left to right, as an example. Anyway, so that's just a couple details to fill in at the end of this discussion about an ellipse. But other than that, we use this same basic format of an equation, whereas x squared over a constant squared, y squared over a constant squared equals 1. And then that's always going to give you an ellipse around 2 foci. So any questions about any of that before we move over to hyperbola? Looks like we have a half hour. Let the games begin again. Okay, so luckily for a hyperbola, we have sort of very, very similar situation to an ellipse. But again, we have a different shape. If you think back about the conics we looked at in the original situation, you have the cone sliced on the top and the bottom, so you get 2 different parts of the graph. And so let's begin, as we did with the others, by talking about physically how you have a set of points. So what do we start with? Just like with an ellipse, you simply start with any 2 points. So let's see. Something like this. And again, these are going to be the foci. So an ellipse has 2 foci, and a hyperbola also has 2 foci. So for an ellipse, we looked at the set of all points that had a constant sum of distances to the two foci. So for a hyperbola, it's going to be a constant difference. So consider all points such that the absolute value of d1 minus d2 is constant. So d1 is the distance to focal point 1, d2 is the distance to focal point 2, and you're going to have some constant difference between the two. So let's use a specific example to think about how this would generate a set of points and how that would generate a hyperbola. And then we'll look at an equation and we'll label some A and B and C and axes and everything. Okay. So let's consider maybe this point here. So if I'm at this point, then D2 is equal to 3. And D1 is something I have to count, is equal to 9. So for that point, the difference between D1 and D2 is 6. So let's say that we're going to go with that. Let's say we're going to consider all points in which the absolute value of the difference in the distances is 6. Whoops, well, that kind of looks good, I'll leave it. So there would be an example. Similarly, in a symmetric way, the difference between the two in absolute value would be 6 if I went to this point over here, where it was 3 away from F1 and 6 away from F2. I'm not liking that other point. Too fat. And as I mentioned before with an ellipse, if I immediately moved left or right horizontally from either of these points, the set distance would be greater or less than 6. The set difference of the distances would be greater than or equal to 6. So I need to move up or down in some way. And if I move straight up or down, again, they'll both grow. But here's what you end up getting. As you move up from the one on the right, the points that have a constant difference of 6 end up veering off this way. And similarly, if I go down to the left, let's get my scratch work out of the way. So again, what is it about these points that I'm trying to highlight in here? Again, it may not be accurate, but if I take one of these points, that this distance has now gotten bigger, D2 has gotten bigger, but F2 has also gotten bigger. And as I go farther out here, they both continue to get larger and larger. So they're both getting larger, but what's important is that the difference between them is staying 6. And in a similar way, I could do the same thing over here, or over here. And you get a hyperbola. So a hyperbola will be these two U-shaped arcs or graphs put together. And I have to be important to point out that these U-shapes are not parabolic. So these are not in the shape of a parabola. They have a basic U-shape, but it's not, it is not a parabola. And the reason for that is because as you go wider and wider with a parabola, the curves get steeper and steeper and go, and curve more and more. But for hyperbola, that's not true. Both of the outside lines or parts of the curve for the U shape are they're asymptotic to a line. So let me sketch that in. So you can imagine that there's a line this way. Didn't drive those too well. And that there's another line this way. And so that the hyperbola, basically the points of the graph of a hyperbola, are settling into this line. They're getting closer and closer to that line. They're asymptotic to these two lines in this cross. Where the center of these two lines, not very well drawn in my picture, the lines should go right through those two. And they'll, of course, have much better pictures in the book. Okay, so again, the concept is that if you begin by simply plotting any 2 points, then from those two points, you can define the set of all points where the difference between the distances to those 2 points is some constant number. That if you take the bigger one, the bigger distance minus the smaller distance, if you always get a 6 or a 10 or some set distance, then you will get a hyperbola. All the points that satisfy that condition form a hyperbola. And a hyperbola has these two U-shaped arcs where the tails or the sides of the U's are both asymptotic to a pair of crisscrossing lines, the asymptotes of these lines. So those are the physical properties. So now what we need to do is we need to label stuff so that we can make a connection to an equation and do the same things we did with the other graphs. All right, so I'm going to take away this nasty sketchings to go back to my graphing system above so we can label things with actual letters and stuff like that. Okay. Okay, so let's start with the idea of having foci, and let's have them be equidistant from the center. I'm going to put one here, one here. So if these are my foci, this is F2 and F1. And the center of hyperbola will be the point right in between those. And again, this will not be a point that's actually on the graph. So we're going to consider the length from the center out to the foci like we did before. We're going to call that C. And so we're going to have a focal length. And again, that's going to be this C value. So then we're going to have, I'll put it in here, a couple of points in between the foci, which are on the hyperbola in a symmetric way. In this case, what's my constant difference in the distances? 8 minus 2, 6. This is also a 6. Okay, I was trying to do that. Wasn't sure if it came out right. Looks like that's what I wanted. Okay, so here I have a situation where I have two focal points, and I say, consider all points where the difference in the distances is 6. And so these 2 points show up. And so that's going to give us a new length. So I'm going to draw this length this way. Oops, that was not what I meant to do. Point here. So we have this length over here. So this, well, so first of all, these points are also called vertices. So the center points of a hyperbola, the points that are closest to each other on the two arcs are called vertices. So we have vertices. Again, that's the plural for vertex. So there's a vertex on the right and a vertex on the left. And so C is the distance. C is the focal length. And so usually we have A to represent the length from the center to one of the vertices. So here we also have an axis. So you could think of this as like half of the axis length or something. I'm just going to write it as distance to vertex from the center. That's going to be our A value. So I'm going to draw in my lines here. Okay, I wanted that to be red. There we go. Okay, I think that's right. Figured I'd draw them in first this time so that they come out a little better. So then my hyperbola will be points from the vertex that leave and come out and start to go asymptotically to these lines. Something like that. All right, so I put this in here because then we can see our B value that we have to define. We're going to have an A, B, and a C. So our B value is going to be the distance from vertex up, meaning horizontally, to the asymptote. So in the picture, that's this distance. And C is looking a little confusing here. So let me relabel C in a more clear way. So again, C is this total length here. That's C. C is the focal length. So it's the distance from the center out to the focus. A is the length from the center out to either vertex. And now B is this up and down or vertical length from the vertex up to the line that's the asymptote for the graph. So that's B. So it just so happens that the focal length C is also the diagonal length from the center to where B hits the line. So this length here is also C. So that's the relationship in the line. The asymptotic lines happen to have a slope where you have basically the rise is B and the run is A, because remember in this triangle, this A here is the distance out to the vertex. So this equation for this line, since it goes through the origin, is y is equal to b divided by a times x. And the equation for the left line, since it's downhill, is y is equal to negative b over a times x. And so, yeah, when we have this relationship, it also turns out that if you make a right triangle of a and b as the base and the side, then the c value is the hypotenuse. So in this case, we get our typical Pythagorean relationship that a squared plus b squared equals c squared. So again, this graph is generated because you had two focal points and you said, consider the set of all points where the difference between the distances to the focal points is a constant. And if you do that, you get two parts to the graph, these two U-shaped arcs, and both of them have a vertex along this center axis. That's the line that runs through the foci. And then from there, as you spread out, the curves approach asymptotically to these two lines, y equals b over a minus x and y equals negative b over a minus x. Questions, comments, discussions about the setup before I then give us the equation for this? So this graphically is probably a little harder to understand the dynamics than either the parabola or the ellipse. That's why I do it last. But we do have similarities. We're still going to call C the focal length. You still have A being sort of half of the axis. In this case, the major axis length. There's only one axis. A is still half of that axis length, the distance from the center out to the vertex along the axes through the foci. And then B is a little bit less obvious in the picture. It's the sort of the rise over the run of A that the asymptotes have as a slope. So let me just sort of point out that separately. So we have slopes of the asymptotes are plus or minus B over A. So the positive B will be the one going up to the right, and the negative B will be the one going down to the right. So just pointing that out. You can see it in the equations above, but just making that clear. Okay, so let's look at the equation. So the equation format is almost the same as for an ellipse. For an ellipse, it was the points that the sum of the distances to the focal points are constant. And for a hyperbola, it's the points where the difference between the distances of the focal lengths is a constant. For an ellipse, we had x squared over a squared plus y squared over b squared equals 1. So if you change to hyperbola, instead of having a sum, you have a difference. So you literally change the plus to a minus in the equation for an ellipse, and you get the equation for a hyperbola. And that's, of course, because in one case you have a constant sum for an ellipse, so you have a sum. And in the equation of a hyperbola, you have a constant difference, so you have a difference. And everything else is the same. Whoops, minus. Okay. So what we want to be able to do, as we did with the other case, is we want to be able to have information about the graph convert into an equation, and information when given an equation to be able to use that to get information about the graph. So we'll do an example of that. And yeah, we have like less than 15 minutes left. So I'll do an example or two of that, and then we'll have to finish. So maybe we'll just say for Wednesday, if you can continue with the rest of the section, where they talk about something called eccentricity, which is just a definition of something. And then they look at how to express conics using a polar graph. They just do that in a theorem. It's on one page, and then they're done with the section. So I didn't quite get to those today. But let's nonetheless do some examples here. Can I fit this below? No. So I have to erase this. These are fatter. Okay, let me just ask real quick. Are there any questions about any part of this picture, this graph, or the equation before I erase it to do a couple examples? Nope, okay. Okay, so I guess I'll leave that there. Let's grab some examples. So I'm looking at, now we've moved over to page 751. Sketch a graph of the following hyperbolas, specify the coordinates of the vertices, the foci, find the equation of the asymptotes, and then using a graphing utility to check your work. All right, so let's maybe take a look at one that's not as straightforward. And you may have this kind of variance in an ellipse problem or a parabola problem as well. So I'm not doing the simpler of the examples, I'm doing a little bit harder one. So it has 25y squared minus 4x squared equals 100. So they're giving us an equation, and the graph is of a hyperbola, but it's not in the standard format. So let's put the format up here. I had x squared over a squared minus y squared over b squared equals 1. So if they give you an equation like this where there are no fractions in it, they basically cleared the fractions. But we want to have the format with the fractions in it so we can identify a and b of our graph. So we need to put the fractions back. And so the basic way to do that is to divide out both sides by the constant on the right, because we know we need to have a 1 over there. So I would start this by dividing both sides by 100. And again, I'm doing this because then I'll have a 1, and then I can distribute and have it in fraction form. So if I do that, I get y squared, 25 goes into 100 4 times, minus x squared, 25, 4 goes into 125 times, equals 1. So we had to do a little bit of a manipulation here to get it into a format. Now, another thing to take note is that in the equation we started with, x is on the left and y is on the right. Whereas in the equation we're given in this problem, y is on the left and x is on the right. And so the difference is when you switch the x and the y, just like with the ellipse, that instead of something that the emphasis is left to right, now the emphasis is up and down. So a hyperbola where it's x squared minus y squared will be the u's opening to the right and to the left. But if you have an equation with y squared minus x squared, then the u's are going to open up and down. Now, again, we can use this. We now can see sort of an a value and a b value. And so this is a squared and this is b squared. And so you can maybe plot some points to start to sketch your graph. So one of the simplest ways to see is that if I plug in for the lead variable the value to match the denominator, then the other variable has to be 0 in order to get a 1. So this tells me sort of right away that I can get the point where I plug in a 2 for y and a 0 for x, or a -2 for y and a 0 for x. Because in this case, my a value is 2, and so that's the distance along the axes from the center up to the vertices. So that means I have a point here, and I have a point here. So these are vertices. And that's because you have y now being your a value, being your distance in the y direction instead of in the x direction. So now I also know that b is the distance I would move in the other direction to get my asymptotic line. So in this case, b is equal to 5. So that means if I go 5 to the right, 1, 2, 3, 4, 5, and a value is 2, that I have a point here. So that means my lines are going to go through there. So let me do this. It's through here. And then I have another point over there, 2, 1, 2, 5 here. There we go. Except I missed my point. There we go. And so similarly, this line would go through the one below there. And this line will go through the point over there. That missed. Whoops. There we go. 1, 2, 3, 4, 5, 2 is there. And 1, 2, 3, 4, 5, 2 there. All right. So in this case, I'm setting it up so that my a value is here. I'm sorry, not my a value. My b value is here, is 5, and my a value here is 2. Then I have this, makes it easier for me to sketch a graph going out and being asymptotic to these lines. And we're supposed to identify some key points. So it says to specify the coordinates of the vertices. So my vertices are here, and they are pictured in the graph. The foci. So to figure out the foci, I need to find the c value. So I know that c squared is equal to a squared plus b squared. So that means that c is equal to the square root of 29, which is a little bit more than 5. And so that means I'm going to go up here, about here, plot a point there, down here, and I'm going to label those. So this is going to be 0, square root of 29, and 0 minus square root of 29. So those are my foci. This is my vertex. And we're supposed to give the equations of the asymptotes. So my asymptote, again, it's through the origin. So this is y, and this is a rise over run of 2/5, 2/5 x. And then this one would be y is equal to minus 2/5 x. So I took one of the tougher ones because instead of being left and right, it was up and down. So we had to reverse a couple of things. But if you do that graphically, hopefully you can follow along. Also, it wasn't given in the fraction form. We had to divide both sides by 100 in order to sort of set it in the format that we're used to. But this is still a good example of being given an equation for a hyperbola, being able to sketch a graph, and being able to identify the vertices and the foci and the asymptotes. Questions, comments, discussions about that? Any part I should explain better or elaborate on if I lost you? Okay, so there's about 2 to 3 minutes left. So won't have time to do it, but the next example, just right from where we left off here, would be instead of being given an equation and identifying key parts of the graph, what if they told us key parts of the graph, like the vertices and the foci or something like that, for a hyperbola, and asked us to come up with the equation? So the thing to note is that to give an equation, the only thing you need to know is what is the a value and what is the b value, and is x squared on the left and y squared on the right, or vice versa, by which way it's going. So if the foci are lying on the same horizontal line, left to right, then it's like this. If the foci are lying on the same vertical line, then the y squared is in the lead. And you know that a squared plus b squared equals c squared. So if you are given an equation and you can figure out the a and the b because they give you a vertices, that will give you the a length, or they give you the foci, that will give you the c, then you can come up with the b value, which you would need for the equation.